Welcome to the Creative AI Podcast. Having a machine identify an object within an image has made significant progress over the years. However, researchers are continuing to work on how to make this happen more accurately and faster and ultimately cheaper. One way of doing that is improving the training data. In their research, we see how the baseline object classification is applied to an image. And in most cases, it covers a part of the intended target, but often missing a couple key details. By adding a modest annotation input from humans, and in this case asking one or two people to click on an object, they've been able to reduce total annotation time by approximately 10x. There's this example that we talk about in the podcast that is this image of two cats. And using the baseline object classification, we see that one of the cats, the cat on the left, has been identified. There's a red bounding box that's approximately half the cat, the front half of the cat. With one click, there's a second bounding box, which is based on their research, which is using most of the cat, and it's missing a little bit of the tail and the top part of the two ears. With a second click, the object classification that the research that we're talking about today then bounds almost the cat perfectly. There's another example of the same process with a bus, where the baseline object classification identifies the entire image of having a bus. One click really zooms it in, a second one perfectly defines what that bus is. And so I think this research is really great because it enables a lot of different parts of the infrastructure of the entire industry to continue to grow. And so by having better training data and faster, cheaper ways of accessing that training data, it allows other people, and we'll talk about some of the applications such as autonomous car manufacturers and people working on that technology, to get the data that they need to continue to train the models that they're working on. So it's really cool research. I'll let Dimitri and Vito talk about it more. Let's hop into the show. Welcome to the show, and I'd love to hear what this research is to you.
Hello. Thank you very much for the invite. This paper is about training object class detectors with click supervision. So traditionally, to train an object class detector, you need a large pool of training images annotated with bounding boxes. So the traditional way that people do this annotation is by drawing manually bounding boxes, and this task is very time-consuming and very expensive. So in this paper, we propose a new way for annotating images, where we have annotators to click on the center of the instances. We use this information in a multi-instance learning technique to obtain automatic annotations for like bounding boxes for the instances, and at the same time train an object class detector on them.
Cool. And I'm going to share my screen and pull up a little bit of an example so the audience is getting a sense. I'm going to pull up the paper first here. So these bounding boxes that we're talking about, I'm going to scroll down a little bit. So we're trying to get these bounding boxes by having a user actually click on them. Is that kind of same way of saying that?
So perhaps I pick it up. Chad, if you zoom on exactly one of these, so we see it big.
Okay.
Any of them, really. Let's say the cat.
Perfect.
This is a YouTube cast, right?
Yeah.
So you see, there are many boxes you see here. Let's say the green box is the correct one. So you see, this box covers the total spatial extent of the cat. It contains the cat completely, but still it's the smallest possible box that does contain it. So this is the exact thing we want. We want a small rectangle that contains the entire cat. And it seems a bit of a weird thing to do, but this is the format by which computer vision models can learn object detectors from. Then this is important because when you then get a new test set, for instance, you want to search for cats in your holiday pictures. So when you are in that situation, then you need to have a detector trained on this kind of data in order to find cats. So what we did in this work is that instead of requiring to draw that green rectangle you see, which takes a long time, we ask humans to just click in the middle of it, in the middle of an imaginary rectangle that's not there when they do it on Mechanical Turk. And it turns out that through the techniques we developed in this paper, it's possible to derive the full extent of the cat just from that one click.
And so it's this idea of saying, hey, if I click on the cat, then the work that the research you guys worked on is going to try to get that optimal box around the entire cat.
Exactly.
That's it.
Okay, cool.
And that takes much less time to do.
Right, totally. Then actually drawing out kind of the four sides of the actual square, right?
Mm-hmm.
And this might be kind of a layman question or a question that the audience might be thinking about, but why does machine vision need the rectangle square on it? Could you take us through a little bit of that piece?
So this is related to the type of output that you need. So what would you find more natural? Because I get this question often. They think with this rectangle, it's a strange thing to do. What would you think would be a normal input?
Yeah, I think it's a great question, because when you get pushed into that answer, I try to think, okay, what would I want to know? And I guess the kind of the maybe non-intuitive or my quick reaction is draw out the cat even more detailed, right? It's saying, hey, how do I get rid of the entire background and just isolate? So I guess that would be my answer.
So that's exactly the right answer. So computer vision models works best in the scenario you just described, when people draw a whole outline around the whole cat, including the pointy ears and every whisker and every paw and all the hair. If you outline the entire cat and all the background is gone, you have a mask, segmentation mask. That's the name the computer vision researchers give. If you have that, you can train the best object detectors possible. But that takes ages. It's in the minute range for one of them. So the second best thing you can do is to at least get this box. And the box tells you a sense of scale. How big is the cat? And that is useful for the computer to learn to localize cats in images and get a bit about how big they are and get a bit the whole extent to that point. And this is quite useful if you want to answer a question, is there a cat in an image? Then you don't need that. But if you want to do things like, give me all the pictures where my cat is drinking milk, or my cat on top of the television. I don't know if you have pictures like that, but whatever. If you want to answer spatial questions, you need a machine that gives you spatial answers. And that's why we need this type of outlining, which is very expensive, or at least a box that's a little less expensive, but still it's spatial in the image, not just an image level.
Yeah. And is that something that it's almost like the background is kind of on average a background, if that makes any sense? And so the machine vision is starting to kind of pick up the what's different from a background to a cat?
Yeah, actually, when you train an object detector, you try to understand what's the foreground and what's the background. And the foreground in this case is the class, the category of the one that you're trying to find. And practically, you try to find to learn an appearance model for this class. So the class looks like that, and the background is different from this one. And actually, what we do the recent years in computer vision, at test time, you have a lot of object proposals in the images. So some regions and some boxes where some objects may be there. And actually, you evaluate all of them according to the appearance model that you learned for this class. And practically, you score them and you say, okay, this looks like a cat, or this doesn't look like a cat. So actually, the background is not the cat, right? If you do it for this class. But actually, you can do it like for all the classes at the same time and try to score like this object proposal as either a cat or dog, I don't know, a laptop, a computer, a headset, bookshelf, or background.
Yeah. And one area that I've seen these little squares rolling around is, you see some of the autonomous car technology, and they try to show what the actual computer is seeing. And I see these little boxes of another car and a bike. Is that a similar process that's going on in the autonomous vehicles?
No, definitely. It is very much the same process. In fact, autonomous vehicles are becoming powerful enough on their own that they are actually running the same algorithms these days as you can run on a desktop. But yes, it's the same conceptually, the very same process. These things you see in the videos about autonomous vehicles, they are the output of the algorithm after it has been trained, when it's localizing new instances of that class through the technique Dimitrios described. basically by evaluating a discriminative classifier at various possible regions in the image. But to train that classifier, you need these training bounding boxes, and that's where our paper comes in.
Right. And so, yeah, so it's this input process. It reminds me of kind of oil, right? You have crude oil, and then you actually have to refine it, and then you can put that into airplanes and jets and cars. And this feels like a little bit of that refining process of saying, hey, we have all this raw data. We need to turn that into interesting algorithms. This is a tool in which to refine that oil a little bit easier for analogy out there.
Maybe, yeah.
And my coworkers will validate that I love making analogies, and a lot of them are shitty. So I appreciate your patience with my analogies. But what would you have an analogy for that, or am I thinking about it in the wrong way?
I'm not sure.
Come up with an analogy.
I'm not sure.
I won't put you on the spot to come up with an analogy.
I mean, actually, your analogy with the oil sounds like the engine is already there in your analogy, and the oil makes it run smoother. Whereas here it's more, like you have a car and it doesn't know what to do at all, but it has the engine and the software is missing. That's more the thing.
Right.
It's more, or the driver.
The driver.
The understanding of the world and what to do is missing. It's more like a robot with no memories or with no program. So these machine learning tools, they learn from this data in order to recognize the world, and that's perhaps acts as, well, it would act as a driver if it was a reinforcement learner.
Yeah.
It's not quite there. But perhaps a better analogy would be more like putting knowledge inside an empty brain. The robot doesn't know anything, and this is a technique to quickly transfer knowledge from the mind of the humans into the mind of the robot. That's perhaps.
Yeah. Okay. I appreciate you sharing. It's always helpful to kind of think about it in an analogy perspective. This feels like a thing that you were saying. Hey, I feel like. Let me take a step back. What triggered the research? I have some suspicions, but I'd love to just hear in your own words. What triggered saying, what if people just click stuff and made that even faster?
Yeah, I'm not really sure how we started exactly this project. So generally in my whole PhD, well, I work on computer vision, and especially on trying to find efficient methods to annotate instances in order to train all these object detectors. So in the beginning, I tried myself a click around, and I realized that it's really, really fast. And people can find this sender of the object very accurately and really, really fast. And then we had this idea how we can feed all this information to a technique that outputs these bounding boxes. And yeah, the technique is very efficient. And actually, it's very accurate. And the output that you get at test time, if you train our machine with our boxes, it's almost as accurate as a machine trained on all these manual bounding boxes drawn by humans.
Let me take a moment to say that this wouldn't be possible without companies like Amazon.com. If you have experience with machine learning and are looking for a new challenge, they have over 100 opportunities available. Be sure to check out the link in the description, and let's get back to the show. And I'm going to reshare the screen that we were looking at before, and we were talking about the cat in the green rectangle and the red. What is the difference between the red rectangle and a green rectangle and the yellow dot here that we're looking at? And just for the people listening, what we're looking at is a bunch of different photos of objects with a yellow dot on an object that is kind of classified, and then there's these bounding boxes around it. And so I'll try to explain for the people who are listening, but what are the differences between the green and the red? And obviously the yellow dot's the click most likely, but what are the differences?
Okay, can you zoom in? Maybe it will be...
Yeah, let's zoom in the cat again.
Let's go back to the cat, all right.
So let's start from the dots. So above you can see only one dot, while below you can see two dots, right? So let's start from the image above. There is only one dot in the instance of a cat, in the center of the cat, and that's the input of our algorithm. The blue box is the output that we get if we use this click inside the algorithm. The red one is what one can have from a weakly supervised object localization technique. So the recent years, there is this line of weakly supervised techniques where people try to train object detectors from a set of images, knowing as to containing an object class. So we have a training set, we have images, and we know for these images that there is a cat in this image or not. So annotators should answer only a binary question. The location of annotation of the object is not there. So people use these techniques to generate bounding boxes automatically. And you can see that the result that you get in this image is this red box, which is not actually accurate. If you go to, if you see the image below, it has 2 clicks. Actually, these are 2 sender clicks from 2 different annotators. We realized that sometimes annotators do some errors when we ask them to click in the sender. And actually, this error is based on the scale of the object, of the area of the object. So, for example, if you see the bus example on the left, there are 2 clicks as well, but pretty much on the same pixel, because the object is very, very small. So when you ask somebody to click on the center of this bus, probably they will click at the same point. But the cat is bigger, so people do some errors, and there is a distance between these 2 clicks. So what we did with these errors was that we use this distance between this, we use this error actually to estimate the scale of the object. And as you can see, it improves a bit the model with the 1 click, which was the blue window, and it finds this green window in this this green box, sorry, in this case, which is way better and actually is very, very accurate.
Yeah, so the top image has 1 click, and then the blue box is cutting off a little bit of the ears and whatnot, and then the 2 clicks on the cat, you guys kind of estimated scale a little bit, and then you're able to, the green box then included the ears, which I'm assuming is, you want the box to include the ears, which are an important feature of a cat.
Exactly. In this case, you can see that you have a distance between 2 clicks, so it tries to find a bit bigger box, or in the dog case on the right, while in the chair case in the middle, the 2 clicks are very close to each other, so the model tries to find a smaller box that actually fits around the object.
Let me say something about the dog picture, Chad. So the red box is perhaps the most important box. In fact, like Dimitrios said, that represents a baseline where the only knowledge given to the algorithm is the presence of the dog in the image, or the cat before, so-called weakly supervised. And then the algorithm tries to put a box by looking at consistent appearance patterns across the entire data set. So it tries to go just from an image level label straight into a box. And those methods have typical failure modes, and here you see one. Typically, they go for discriminative parts. So that's also why it gets for the head of the dog, and the body of the dog is not seen as particularly important to recognize dogs. And instead, if you augment those algorithms, that's what we did here, by adding the click to these weakly supervised techniques, then they get more of the full extent. Like you see, the dog image is perfect to explain why it's useful to have the click.
Right. Yeah, and that second one actually, kind of finished out the rest of the dog piece. And I would imagine that 2 clicks and 3 clicks, 4 clicks, 5 clicks, I mean, it's probably a diminishing return on that. But is there kind of did you guys experiment with additional clicks beyond 2?
No, actually, we didn't go there. First of all, adding more clicks doubles or triples the annotation time that you need, right?
Right.
So if you assume that you do like 10 clicks, maybe it's better to draw the entire box, right? Or do something else. I think with 2 clicks, so with 1 click, we can get the location of the object, right? With 2 clicks, we get the scale. Probably if we go to 3 or 4 clicks, we can have a better estimation of the scale, and maybe it can improve a bit better the location, because we can get, for example, the average position of these clicks, and probably the average position would be more accurate than just having 1 or 2. Well, I'm not sure exactly if it will go way, way better, all this estimation of the scale, if we use 3 clicks or 4 clicks. But I'm a bit confident that with 2 clicks is quite okay.
Yeah, I'm getting that sense of the trade-off of having 2 or 3. Probably the diminishing returns is, I mean, we're looking at the proof, right? The 2 clicks have the the cat in the perfect bounding box. And so at what point and why would you need to continue to? So that totally makes sense.
So also in terms, I mean, Dimitrios placed it well. It's about diminishing return. At some point, if you click too much, it's not worth it anymore. But also between 1 and 2, there is a true fundamental difference. It's not only more accurate estimations. The scale of the cat in the blue box, the reason we got it from a single click is because we also look at all the other training images. So there is this recurring pattern phenomena. So whereas in the second, we also have that phenomena, but the 2 clicks fundamentally bring you the scale. Not very accurately, but it gives you a new, qualitatively new information. From 3 onward, you can refine these estimations in statistical terms, but you don't have a new variable that you can estimate.
Right. That makes sense.
So we actually never tried beyond 2. I feel at some point it's not worth it, but I don't know at which point it's not worth it.
Right. And going back to this bus example, and I was meaning to ask this, so the red bounding box was the entire image is saying like, yes, there's a bus here, but with no specifics, right?
Yeah, this is a common error by weakly supervised localization, based only on the image label. All you know, this image somewhere has a bus.
Right.
And then at this point, although it tries to compare across all the entire training set, in this case it failed. This is a common failure mode for purely weakly supervised methods.
Yeah, it really is amazing then how specific the green box is with all of this context of the double clicks of the difference between the red and the green is profound in this example. It's really cool. Cool. So what was the most challenging part for this research as you guys were going through it?
Oh, yeah. I would definitely say the part of collecting and crowdsourcing all this data. So when you're in the lab and have this idea and try yourself to click in the middle and you see that, okay, I'm very fast, I'm very accurate, let's do it. Then when you go to Mechanical Turk and all these crowdsourcing platforms and really try to work with naive annotators and explain them the task and really have them make what you want, it's really very difficult part. So I think that was by far the most challenging part. So in the beginning,
the humans part of it.
Sorry?
The humans were the most difficult part of.
People, that's the problem.
Dealing with machines, it's easy.
It's easy, yeah.
You write your code, you debug it, you get the results.
No, but actually, the Turk part, I totally agree with Dimitrios. So once you go on Turk, these guys, they are very motivated and they learn quick. But the first 2-3 hours they do something, it's so bad. You really need to put effort. In fact, yeah, at Google, we also, now I partially work at Google, we also try to do a lot of crowd computing. And yeah, typically, that's the biggest difficulty. I totally confirm.
Yeah, that's a funny, of all the interviews I've done, I don't think the human aspect has been the most challenging thus far, which is ironic, which I love. So what are some potential applications that you see with the research in the real world and with the community and whatnot?
That's the application that you can have for object detection in general. So as you said before, autonomous driving is one of them. And, you know, we saw all these advances the last 2-3 years, especially in autonomous driving. And, you know, we have almost real cars that have some algorithms implemented. And I'm pretty sure in near future we will have a lot. Then, you know, in any robot that wants to localize objects around and understand the environment, moving it or doing something else, and other stuff like image retrieval, like as we search in Google right now, we can search in code directly. I want this cat that looks like my cat in another image, and stuff like that. It's all about object.
Perhaps another view on this. Our research doesn't necessarily open a new application. It is a fundamental operation to enable to train object detectors from a lot of data. And then all the applications of object detection that you mentioned, retrieval, robots, and self-driving cars are classic, but also aids for the blind. And
yeah.
The point is, the applications are the same as usual, But now you can train from a lot more data because you have to pay a much lower price to train your detectors.
Yeah, it really feels very infrastructure-y, and I think that's really fantastic because the infrastructure needs to come with the applications, and they have to work together in order for us to really change the world. So I totally agree with that, and it makes a lot of sense. What are you excited about next? What are you working on next? What's next in general for you?
What's next? Okay, get my PhD, hopefully. That's next for me.
Yeah.
Well, what's next? I'm pretty sure that some of these ideas can be expanded and be applied in other tasks of computer vision. For example, for semantic segmentation, we went into it a bit before. So in semantic segmentation, at training time, you need images where every pixel of the image should be annotated as a class or a background. So annotating one single image for this task probably takes more than a minute or two or a bit more. So maybe we can apply some ideas of all these efficient annotation schemes to semantic segmentation and try to get segmentation masks from efficient annotations for these images.
I have another future.
Another feature.
Yes.
So basically, okay, yes, sure, you can get more detailed stuff, but for me, the real next big win. So what Dimitris has been doing in a series of papers, including this one, but also before, is cut the unit cost of obtaining one spatial annotation. So this one cat now costs you less than it costed you before. But if you want to annotate 1 million cats, it's still 1 million units. Just one of them is cheaper. So what I really would like to go is really into this active learning dream that's been around for a while, but for object detection doesn't quite work yet, where you get 1 million annotations for a cost which is less than 1 million. So you want to go ideally into something in the square root of n, ideally log n, that would be awesome. And the problem with these things is that in terms of training your detectors, you can do that to some degree, but in order to have a guarantee that the remaining images which you didn't even look at, right? If you're sublinear, some images you don't look at. Do we manage to get a sufficiently high statistical guarantee that these images you didn't look at still have a right box on them? So this would really be the next, because if the unit cost goes down and it scales sublinearly, then we can do billions. That would be cool. It's a lot of work, but
yeah, it's incredible. Yeah, it's big. I like that. Yeah. One thing I want to do before we end is I wanted to show the website that you guys had that was interactive and had some examples and whatnot. And I have it pulled up here, and we have cats. Cats been the theme of the show. But take us through what's different about the website compared to the images in the paper.
Well, actually, it's all of them. All the images we annotated with clicks are there. You can pick a class here. You can download all the data, the clicks, or the output bounding box we have. And you can see the clicks, the output bounding boxes in all the examples. It's about 5,000 images.
And
Cool.
even cooler, if you click refresh image, you get a random sample. Try again. And so for me, this is an ancient dream. I like to give talks where I don't prepare results, so I cannot cheat and show only the good ones. Like in the paper, we show the good ones.
Right.
Here, well, it's random, and it's the entire data set we sample from, so you get all of the truth.
Right. When you see this, is there one that you talked about all the good ones? Is there a representation of one that you're like, I wish it would have done a little bit better?
Yeah, I can see it. For instance, the bottom left cat.
Bottom left, this
No.
one here?
Yeah.
That one is not quite right.
And so then the blue box is the one that we would expect to be even more accurate, right?
Yeah, the blue box is the final output, and the yellow box is the ground truth. So this is the perfect answer.
Got it.
You can unclick the yellow box if you wish. So we know it's correct, so then you can see really just the blue. So not to confuse. Dimitris, at a good level of accuracy, let's say above 50% IOU, what are our localization rates? Are we in the 90-something %?
No.
Not yet.
Not yet.
Now I'm going to open the paper and look at the
we are
plot.
73, 70.
Really? No, I have this plot here. We are at 80 something.
Yeah, 80. Yeah, with 2 clicks, it's 80. Yes.
It's about 80% correct. So you still have some 20% of the cases where the box is not tight on the objects. Perhaps half on it, but it's not tight according to our high standard criteria.
I love one example here, and I don't know if this goes back into the human aspect, but this bottom row right and then the far right middle one, where it looks like the clickers pick 2 different cats, which would definitely seem like a challenge.
Yeah, so because we ask 2 different annotators to click on the middle of any instance of a cat in the image, sometimes if there are multiple instances in the image, they pick a different one. But because, as you can see in this case, so actually in both of these cases, the distance between these 2 clicks is really a lot in terms of pixels, while in all the other cases, it's very small. So in our model, we can handle these cases and automatically assume that these 2 clicks are on 2 different instances, and we try to find one of them.
So in fact, let me add some fun idea Dimitrios had. We actually can train what is the maximum separation after a while. You know, we said that if 2 clicks are far away, the object is bigger, right? But at some point, they're so far away that they are not on the same object. And we can actually, we don't need to guess these thresholds. We can train it from the way the annotators click on objects during the training stage that we do to train the annotators to do the job. So this seems complicated. But basically, on Mechanical Turk, we send the annotators on Turk some trial images for them to understand the task. And from the way they respond on those images, we can learn a statistical model on the association between distance and scale, for instance. But we can also figure out at which maximal distance the 2 annotators actually meant 2 different instances. So we can actually use the human annotator training phase to train the model that then retrain the detector. We thought it was fun.
Yeah, that's super interesting. Cool. So I think that does it. I'd like to give each guest maybe 30 seconds, maybe a minute of anything that you want to kind of soapbox about, or just say to anyone listening, or any way that anyone can help.
Well, so I guess the best way the listeners can help is to keep thinking AI is cool, reading papers and supporting a community. You know, I've been in this game for many, many years, and it's amazing to see. For me, that's the most amazing. The last 2, 3, 4 years, the public interest in this area has exploded completely. And I think that's, in a way, that's the best news that people can do, is to be interested and keep following us.
Yeah.
Cool. I think that's great. Yeah, it's definitely something that has motivated me. And I've been personally inspired by just the more tangible, realistic things that I could see that weren't necessarily a search algorithm being a little bit more intelligent, or, I was reading about Google's Gboard and how they optimize the keyboard process. And it's interesting now that I've gotten into it, but looking at some of these infrastructure pieces and being able to touch and feel it, I think for the layperson is really making it much more accessible. And so it's really cool to have the community be so open to share their research and talk about it. So I appreciate you guys joining the show. And I'll put the link to the actual website in the description for anyone listening. But thank you guys for joining this show, and have a good one.
Hi.
Yeah.
Bye.
Thank you.